Running wiring and ceiling joists for basement renovations offers several advantages. Firstly, simplified installation is a major benefit. This method eliminates the need to drill through studs and fish wires through walls, thus making the installation process easier and faster. Secondly, easier access for servicing is another key advantage. If a device needs to be moved or repaired, the wiring is easily accessible in the ceiling joists, avoiding the need for invasive wall repairs. Thirdly, reduced cable management is achieved. Running wires in the ceiling eliminates the need for exposed cables or wires running along walls and ceilings, resulting in a cleaner and more organized look. Fourthly, there is flexibility for future renovations. If the homeowner decides to change the layout of the basement in the future, the wiring can be easily adjusted within the ceiling joists, minimizing the need for rewiring. However, there are also disadvantages to consider. Firstly, increased cable usage is a potential drawback. This method may require longer cable runs to reach outlets and switches, resulting in higher material costs. Secondly, careful planning is required. The placement of ceiling joists and devices must be carefully planned to ensure proper alignment and avoid conflicts with other building elements. Thirdly, there is a potential for interference. If the ceiling joists are made of steel, they may interfere with wireless signals and affect Wi-Fi performance. Additional considerations are also important. Firstly, verify if your local building codes allow for electrical wiring to be run in ceiling joists. Building codes are there for safety, and adherence to those requirements are a must. Secondly, use fire-resistant cables and protect the wiring from potential fire hazards, such as heat ducts or recessed lighting fixtures. Always take precautions to minimize or eliminate fire dangers. Ensure that the wiring is installed safely and according to electrical standards by a licensed electrician. This is crucial for safety and compliance. When running electrical wiring, it is essential to adhere to the National Electrical Code, or NEC, which provides comprehensive guidelines for safe and effective electrical installations. Several articles and sections within the NEC are particularly relevant to wiring and ceiling joists, and understanding these can help ensure compliance and prevent potential hazards. Article 300.4 addresses protection against physical damage. When running cables or conductors through or alongside framing members, they must be protected from nails or screws that could penetrate them. This typically involves using metal nail plates or running the cables through the center of the framing member. Article 310 covers conductors for general wiring. It specifies the types of conductors that can be used, their ampacity, and conditions for use. Selecting the right type of wire and ensuring it is properly sized for the intended load is critical for safety and performance. Article 314.23 focuses on boxes and fittings. Electrical boxes must be securely mounted and properly supported. When running wiring and ceiling joists, ensure that the boxes are adequately attached to the joists and that they provide sufficient space for making connections. Article 320 pertains to armored cable type AC. AC cable is often used in residential wiring due to its durability and ease of installation. When using AC cable in ceiling joists, make sure it is properly secured and supported at intervals specified by the NEC, typically every 4.5 feet and within 12 inches of each box or fitting. Article 330 covers metal-clad cable type MC. MC cable is similar to AC cable but offers greater flexibility and is suitable for both exposed and concealed work. Like AC cable, MC cable must be properly supported and secured. Article 334 addresses non-metallic sheet cable types NM, NMC, and NMS. NM cable, commonly known as Romex, is widely used in residential wiring. When running NM cable in ceiling joists, it must be protected from physical damage and secured according to NEC guidelines. This often involves running the cable through bored holes or using cable staples. Article 394 pertains to concealed knob and tube wiring. While less common in modern installations, knob and tube wiring may be encountered in older homes. The NEC provides specific requirements for the safe use and maintenance of knob and tube wiring, including proper spacing and insulation. Article 398 covers open wiring on insulators. This wiring method involves running single conductors supported by insulators. It is typically used in agricultural or industrial settings but may be found in older residential installations. The NEC specifies requirements for conductor spacing and support. Section 300.11 addresses securing and supporting wiring. Wiring must be securely fastened to building structures to prevent strain on conductors and connections. This section provides specific requirements for supporting cables and conductors in ceiling joists and other locations. Section 300.14 covers the length of free conductors at outlets, junctions, and switch points. Sufficient wire length must be left at each termination point to allow for easy connections and future maintenance. Typically, at least 6 inches of free conductors should extend from the box. Section 310.15 provides guidelines for determining conductor ampacity. It is crucial to select the correct wire size based on the anticipated load and the ambient temperature. This section includes tables and calculations for adjusting ampacity based on these factors. Section 314.16 focuses on the number of conductors in outlet device and junction boxes. Boxes must be sized appropriately to accommodate the number of conductors and devices they contain. Overfilled boxes can lead to overheating and other hazards. Section 334.30 addresses securing and supporting non-metallic sheet cable. NM cable must be supported at intervals not exceeding 4.5 feet and within 12 inches of every box or fitting. Cable staples or straps must be used to secure the cable without damaging the outer sheath. Section 334.80 covers ampacity of non-metallic sheath cable. The ampacity of NM cable is typically limited to that of a 60 degrees Celsius conductor, unless the cable is marked otherwise. This limitation must be considered when selecting wire sizes for branch circuits. NEC Table 300.5 provides minimum burial depths for underground wiring. While not directly applicable to wiring in ceiling joists, it is essential to understand the requirements for any underground wiring that connects to the basement. This table specifies burial depths for different types of wiring and applications. NEC Table 310.16 provides allowable ampacities of insulated conductors. This table lists the ampacities of various conductors based on their insulation type and temperature rating. It is an essential reference for selecting the correct wire size for specific applications. NEC Table 314.16 lists the number of conductors allowed in standard boxes. This table helps ensure that boxes are not overfilled with conductors, which can lead to overheating and safety hazards. NEC Chapter 9 contains tables and examples for calculating branch circuits and feeder loads. These calculations are essential for determining the appropriate size of conductors and overcurrent protection devices for electrical circuits. When planning and executing electrical wiring in ceiling joists, it is also important to consider the following safety measures. Firstly, always disconnect power before working on electrical circuits. Turn off the circuit breaker or remove the fuse that supplies power to the circuit you will be working on. Secondly, use appropriate personal protective equipment. Wear safety glasses, gloves, and insulated tools to protect yourself from electrical shock and other hazards. Thirdly, inspect wiring and equipment for damage. Before installing any wiring or equipment, inspect it for signs of damage such as frayed insulation or cracked housings. Do not use damaged wiring or equipment. Fourthly, follow manufacturer's instructions. Always follow the manufacturer's instructions for installing and using electrical wiring and equipment. Fifthly, use the right tools for the job. Use the appropriate tools for cutting, stripping, and connecting wires. Using the wrong tools can damage the wiring and create safety hazards. Sixthly, make sure connections are secure. Ensure that all wire connections are tight and secure. Loose connections can cause overheating and electrical fires. Seventhly, test your work. After completing the wiring installation, test the circuit to ensure that it is working properly. Use a multimeter or circuit tester to verify that the wiring is properly connected and that there are no shorts or open circuits. Eighthly, label circuits clearly. Label all circuit breakers and outlets clearly so that you can easily identify which circuits they control. Ninthly, keep wiring organized. Keep wiring neat and organized to prevent damage and make it easier to troubleshoot problems in the future. Tenthly, consider future needs. When planning your wiring installation, consider your future needs and plan for additional capacity if necessary. Overall, running wiring in ceiling joists can offer significant advantages in terms of installation simplicity, serviceability, and flexibility. However, it is important to weigh these advantages against the potential disadvantages and ensure that the installation is done safely and in accordance with building codes. In residential electrical systems, understanding voltage drop is crucial for ensuring efficient and safe operation of electrical devices and appliances. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can lead to several problems, including reduced performance of electrical equipment, overheating of conductors, and potential safety hazards. Several factors contribute to voltage drop in residential wiring. These include the length of the wire, the gauge or size of the wire, the amount of current flowing through the wire, the type of conductor material, and the temperature of the conductor. Longer wires have higher resistance, which results in greater voltage drop. Thicker wires have lower resistance and therefore less voltage drop compared to thinner wires carrying the same current. Higher current flowing through a wire causes a greater voltage drop. Copper conductors have lower resistance than aluminum conductors, resulting in less voltage drop for the same wire size and current. Higher temperatures increase the resistance of conductors, leading to increased voltage drop. The National Electrical Code, or NEC, provides guidelines for acceptable voltage drop in residential wiring. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual outlets, lights, and appliances, while feeders are the circuits that supply power to branch circuits. To calculate voltage drop, you can use Ohm's law and the following formula: voltage drop equals current times resistance, where voltage drop is the voltage drop in volts, current is the current flowing through the wire in amps, and resistance is the resistance of the wire in ohms. To determine the resistance of the wire, you can use wire resistance tables provided in the NEC or online calculators. These tables list the resistance per unit length for different wire sizes and materials. The NEC provides several examples and guidelines for calculating voltage drop. For example, consider a 120 volts branch circuit supplying a load of 10 amps over a distance of 100 feet using 14 American wire gauge or AUG copper wire. Using wire resistance tables, the resistance of 14 AWG copper wire is approximately 2.53 ohms per 1000 feet. Therefore, the resistance for 100 feet of wire is 0.253 ohms. Using the voltage drop formula, voltage drop equals 10 amps times 0.253 ohms equals 2.53 volts. The percentage voltage drop is calculated as voltage drop divided by source voltage times 100 equals 2.53 volts divided by 120 volts times 100 equals 2.11%. Since the voltage drop is less than the NEC recommended maximum of 3%, the wiring is acceptable. To minimize voltage drop in residential wiring, consider the following strategies. Use larger wire sizes. Increasing the wire gauge reduces the resistance and therefore the voltage drop. Keep wire runs as short as possible. Shorter wire runs minimize the total resistance and voltage drop. Balance the load on circuits. Distribute the electrical load evenly across different circuits to avoid overloading any one circuit. Use copper conductors. Copper has lower resistance than aluminum, so using copper conductors can reduce voltage drop. Install additional circuits. If necessary, install additional circuits to reduce the current flowing through each circuit. Regularly inspect wiring connections. Loose or corroded connections can increase resistance and voltage drop. Ensure that all connections are tight and clean. In addition to voltage drop, other electrical considerations are important to consider when running wiring in ceiling joists. Firstly, grounding is essential for safety. Grounding provides a low resistance path for fault current to flow back to the source, which helps to protect against electric shock. Ensure that all electrical boxes and equipment are properly grounded according to NEC requirements. Secondly, overcurrent protection is critical for preventing overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Select the appropriate size overcurrent protection device for each circuit based on the ampacity of the conductors. Thirdly, GFCI protection is required in certain locations where there is a higher risk of electric shock, such as bathrooms, kitchens, and outdoor areas. GFCI outlets and circuit breakers are designed to detect ground faults and quickly interrupt the flow of current, which can help to prevent electric shock. Fourthly, SI protection is required for branch circuits that supply power to bedrooms and other areas where arc faults are more likely to occur. SI circuit breakers are designed to detect arc faults, which can cause fires and quickly interrupt the flow of current. Fifthly, surge protection is important for protecting sensitive electronic equipment from voltage surges caused by lightning strikes and other electrical disturbances. Surge protectors can be installed at the service entrance or at individual outlets to help protect against damage from surges. Sixthly, proper box fill is crucial for ensuring safe and reliable wiring connections. Electrical boxes must be sized appropriately to accommodate the number of conductors and devices they contain. Overfilled boxes can lead to overheating and other hazards. Seventhly, cable management is important for keeping wiring neat and organized. Use cable ties, straps, and other cable management products to secure and organize wiring runs. Eighthly, labeling is essential for identifying circuits and equipment. Label all circuit breakers, outlets, and other electrical components clearly so that they can be easily identified. Ninthly, documentation is important for keeping track of wiring installations and modifications. Maintain accurate records of all wiring installations, including circuit diagrams, wire sizes, and overcurrent protection device ratings. Tenthly, inspections are important for verifying that electrical installations are safe and compliant with building codes. Schedule regular inspections by a qualified electrical inspector to ensure that your electrical system is in good condition. The type of wiring used in a residential electrical system can affect its performance and safety. Non-metallic sheath cable, or NM cable, is the most common type of wiring used in residential construction. NM cable consists of 2 or 3 insulated conductors enclosed in a non-metallic sheath. It is relatively inexpensive and easy to install, but it is not suitable for use in damp or wet locations. Metal-clad cable, or MC cable, consists of insulated conductors enclosed in a flexible metal sheath. MC cable is more expensive than NM cable, but it provides better protection against physical damage and is suitable for use in exposed locations. Armored cable, or AC cable, is similar to MC cable, but it has a spiral metal armor that provides even greater protection against physical damage. AC cable is often used in commercial and industrial applications. Conduit is a rigid or flexible tube used to protect electrical wiring. Conduit is often used in locations where wiring is exposed to physical damage or moisture. Electrical metallic tubing, or EMT, is a thin-walled steel conduit that is commonly used in residential and commercial construction. Rigid metal conduit, or RMC, is a thick-walled steel conduit that provides the greatest protection against physical damage. Flexible metal conduit, or FMC, is a flexible metal tube that is used to connect electrical boxes and equipment. The color coding of electrical wiring is important for identifying the purpose of each wire. Black wires are typically used for hot wires, which carry current from the power source to the load. White wires are typically used for neutral wires, which return current from the load to the power source. Green or bare copper wires are used for grounding wires, which provide a low resistance path for fault current to flow back to the source. The size of electrical boxes is determined by the number of conductors and devices that will be installed in the box. The NEC provides guidelines for calculating the minimum box size based on these factors. It is important to use the correct size box to ensure that the wiring connections are safe and reliable. The spacing of electrical outlets is governed by the NEC, which requires that outlets be installed so that no point along a wall is more than 6 feet from an outlet. This helps to ensure that extension cords are not used excessively, which can create safety hazards. The height of electrical outlets is typically 12 inches above the floor, but it can vary depending on the application. Outlets in kitchens and bathrooms are often installed higher to protect them from water damage. The type of electrical panel used in a residential electrical system depends on the size of the home and the amount of electrical load. A typical residential electrical panel has a capacity of 100 amps to 200 amps. The electrical panel should be located in a readily accessible location, such as a utility room or garage. The proper use of electrical tape is important for insulating and protecting wire connections. Electrical tape should be applied tightly and neatly to cover all exposed wire. Avoid using excessive amounts of electrical tape, which can create a fire hazard. The safe use of extension cords is important for preventing electrical hazards. Extension cords should only be used temporarily and should not be used to supply power to multiple devices. Avoid overloading extension cords, which can cause them to overheat and start a fire. The importance of regular electrical inspections cannot be overstated. Regular electrical inspections can help to identify potential hazards and ensure that the electrical system is in good condition. Schedule inspections by a qualified electrical inspector every few years to ensure that your electrical system is safe and compliant with building codes. In conclusion, when running wiring in ceiling joists, it is crucial to consider both the advantages and disadvantages, adhere to the National Electrical Code, and implement safety measures to ensure a safe and reliable electrical system. Understanding voltage drop, wire types, box fill, and other electrical considerations is essential for a successful installation. Remember to always consult with a licensed electrician for professional guidance and installation to ensure compliance and safety.